functions are functions that are polynomials divided by a polynomial. And a polynomial is an algebraic expression in which the exponents on the variables are whole numbers. So if I have a function that is a polynomial divided by a polynomial, or is an expression that I can write as a polynomial divided by a polynomial, then it's a rational function, and I should fill out this outline of information before I go and graph it, or even before I use too much off of my graphing calculator. Now in this example, we're going to do the graph of a rational function that actually has a hole in the graph. There are other things that might happen with rational functions, and I've made video segments for a lot of those different types of situations. And I've linked those videos to this video in the description. So feel free to kind of look at the type of rational function that you've been asked to graph or interested in learning more about, and then view the videos to see what specific components or how you might be able to recognize what to do in graphing your rational function. So here, when we're looking to start with, we're going to fill out this outline. Anytime I have that polynomial divided by a polynomial, I should start just writing out the outline of my steps and then going back and filling them in from the specifics of the function that I'm dealing with. So here, my y-intercept. The way you find the y-intercept of anything is take out the x's and put in 0. So remember, f of x is just another name for y, so I'll write y is equal to 0 squared plus 2 times 0 minus 8 over 0 minus 2, and that gives me 0 minus 8 is negative 8, divide by 0 minus 2 is negative 2. Well, negative 8 divided by negative 2 is a positive 4. So I put 0 in for x, and I got 4 out for y. Next up, the x-intercepts. Well, the x-intercepts, you set y equal to 0, and they are the values of x that make the function come out 0, but are also in the domain of the function. So f of x is just another name for y. We're going to put 0 in the left side and write 0 is equal to x squared plus 2x minus 8 over x minus 2. A fraction is 0, will come out to be the value 0 when the numerator is 0 as long as the denominator is not 0. So we're going to take this numerator, x squared plus 2x minus 8, set it equal to 0, and I'm going to solve this quadratic equation. I can solve it by factoring if it factors. If not, I can factor it by completing the square or by the quadratic formula. Now this quadratic expression does factor. It factors as x plus 4 times x minus 2. And then setting each of these equal to 0 and solving, x plus 4 equals 0. Subtract the 4 from both sides. I get x equal negative 4. And then x minus 2 equals 0. Add 2, I get x equal 2. And these are my possible x coordinates of my x-intercepts. But I still need to make sure that they don't make the denominator 0. I need to make sure they're in the domain of the function. Well, negative 4 minus 2 is negative 6. Doesn't make the denominator 0. So I can use that. So it is the ordered pair negative 4 comma 0 for an x-intercept. But 2 minus 2 gives me a 0 in the denominator. So I can't use x equal 2 as an x-intercept because it's not in the domain of the function. In fact, since 2 was a value that made the denominator 0, I know x minus 2 is a factor of the denominator. Since 2 also made the numerator 0, I got that when I worked this through, then x minus 2 is also a factor of the numerator, and I saw it within the factorization. So actually, this function looks exactly like another function that would be easier to graph, except at that point, x equal 2. So when I look at the simplification, I have y is equal to the numerator factors as x plus 4, x minus 2. The denominator is x minus 2. I have a common factor pair of x minus 2's that I can remove as a common factor pair. And now what I have as a simplification, there's nothing in the denominator anymore, or even if there was something left in the denominator, the x equal 2 won't make the denominator 0. So when you have a value of x that in the original function gives you 0 in the denominator and 0 in the numerator, but then once you simplify it, it doesn't make the denominator 0 anymore. You get a punch out hole in the graph there, not a vertical asymptote. So here, I found it out in step 2, just looking at the glitch that happened, but I realized then that I need to make myself a note in step 3 that at x equal 2, there's a hole in the graph. And a hole in the graph happens at an x value that originally made the denominator 0, also made the numerator 0, but once I simplified it, didn't make the simplified denominator 0 anymore. Remember, and just kind of as a review, vertical asymptotes would happen at a value of x that makes the denominator 0, but not the numerator. So just to reiterate that. And in this particular example, I don't have a value of x that would make the denominator 0 but not the numerator. So this particular example does not have a vertical asymptote. Now, once I have denoted that I do have a hole in the graph at that x value, I actually, for the rest of the problem, can graph this simplified equation instead of the original, because the original pictures and this simplified functions picture looks exactly the same everywhere except at x equal 2. So we're going to graph this simplified one and just remember how to compensate for what happens at x equal 2. So for this particular problem now, the thing we're going to graph is f of x equal x plus 4. And after that, we're going to put x can't be 2 from what happened and making sure that we have all the specifics of the original thing that we wanted to graph. So since this particular one, once I simplified it, actually doesn't have a fraction in it anymore, I'm not going to have a horizontal or slant asymptote. It doesn't have the characteristic of a rational function in its simplified form. So my points that I can get here with my x and my y, I can get them from the simplified. So I can plug in values that are smaller than 2 and bigger than 2. And I do have this information that I've already gathered will still be valid in my original, or in my simplified form. See, if I put 0 in for x, 0 plus 4 is 4, I get 4 out for y. So I still have the 0, 4 that I got in step 1. I don't have to throw up my hands and say, oh my gosh, I did all that work and nothing's going to come of it. It still is valid information. In step 2, I got that my x-intercept is -4, 0. Still true. So what I'm going to do is condense this information a little bit, and then we'll graph our rational. So now let's take all of the information that we have and put it on our graph. So we have a y-intercept of 0, 4. So don't go left to right, go up 4. Draw my dot. I have an x-intercept of -4, 0. So go left 4, don't go up or down. Draw my dot. I have a hole in the graph at x equal 2 is what we had before I did the segment to kind of condense this stuff. But remember, it's going to be where this function kind of continues towards. So to figure out where the hole in the graph is, you take your x value that you couldn't put in the original function and run it through what you have for your simplified function, and just remember to put a hole in the graph there. So actually we could do this where we put in like a dashed 2 to remind ourselves that it's going to be a hole in the graph, and then 2 plus 4 is 6, and we can do like a dash 6 to remind us of that. So when I go right 2 and up 1, 2, 3, 4, let's see, 5, 6. So right 2, up 6, I have a hole in the graph. And then if I still put in like 3, it'd be 3 comma 7. So I get that this is a line but the accurate graph of it will show this punch out hole in the graph at the value of the ordered pair 2 comma 6. Now, if you were to graph this function on your graphing calculator, you would see this line, but they would just not be able to show you with the pixels of your calculator screen that there's actually a hole in the graph there. So you wouldn't know to put it on whatever document that you were showing the graph of it unless you did this other work. And also, if you graphed this f of x is equal to x plus 4 part, you would put that in and get this exact same picture, but you'd have to remember that x can't be 2. So if you did graph it and didn't run the 2 through, you'd go 2 comma graph, take your pencil's eraser and just erase out a little bit and do an open circle there to designate that. If you go to your table function, you'll see right across from 2 of this original function, it says error. And that's saying that that point x value could not be put into this function because it's not in the domain. So when we wrote the simplified one, because this had a common factor top and bottom that could be removed, we had to remind ourselves that 2 is not in the domain of the function that's simplified, so that we keep track of how we want to write this so it is the same as the original function and draw an accurate picture. So hopefully that's been helpful in giving you examples of what you would do if there was a rational function that actually had that anomaly that there was a hole in the graph.